Okay, so now let's, as in terms of a demo, I'm going to show you, just walk you through a little bit of what you might expect to see in terms of the files that might be present in a Linux-based operating system. Now, most of you, the first time that you log in, chances are that once you open a terminal, this is probably what you see, right? It just shows you a prompt, which tells you that you are in your home directory, right? Now, how do you know any of that? Well, one of the commands that is useful over here is pwd, print working directory. And it tells me that, yes, I am in whatever has been assigned as my home directory. I can use the command ls, which in turn tells me what files or folders are present in that particular directory which has been assigned to me, right? And there are also certain hidden files. ls-a will tell me that there are more files out here which are not normally shown if I just type the ls command. And that's just to sort of keep things clean. All of this is operating system level stuff, not even operating system. This is what is called the shell level stuff, all right? So the shell is the interface that we directly see when we are typing in commands. It is not the same as the operating system. The shell is only the way that you send commands into the OS kernel, right? The operating system by itself is something that you never really get to see, right? You don't directly interact with it. All your interactions are only by means of various other kinds of commands. What kinds of commands? It's one way of looking at it is to run certain kinds of specialized tools. This command strace is an example of a specialized tool that can be used to get more information about what happens when a particular program is being run, right? So if I just write strace, it tells me I have to give it a program name. So let me try something like strace with ls, okay? And what you can see is it has printed out a whole lot of information out here. So let me go back and sort of see if I can make a little bit of sense out of it. As you can see, it's printed out quite a lot of information. But the interesting thing is every line out here, right, is essentially indicating a function call. So what this strace command is doing is it's telling you what are the system calls that were executed as part of running this ls command. Okay. Think about it. Every one of these system calls is something where the system has moved from user space into kernel space, done something, and then come back. Okay. And as you can see over here, there were a very large number of lines of function calls that were reported. Each and every one of those got executed within a fraction of a second, of course, and gave us the final result, right? So the first one basically says, it is calling an exec. This exec essentially says there is the operating system, which in turn is creating a new process. It is executing a new process. That's the execve function call. There is another function call over here called break, which is used for, it is related to memory management, right? The details don't matter. Similarly, you have something for mmap. You are trying to access certain files, right? All of these, for the most part, are difficult to explain right now. They are related to how the system goes around deciding what extra runtime files or runtime functions are needed, right? So I'm going to ignore most of this. Some of the functions, though, that are useful are, for example, things like you will see that there are many read function calls, and similarly there would be close function calls. Of course, you have to open before you actually go through. You might see that, for example, a file like this is being opened. Why is it being opened? Because this is part of what is the capabilities that the operating system needs to check before it allows a particular program to run, right? So all of these different things are getting executed, right? And finally, if I go all the way down to the end, I will find that there is this write function call, which actually says, okay, this is the output which was generated by that write function call, which in turn is actually what I saw when I ran the ls command, right? So strace can be useful. It is also a whole lot of information. It is tremendously useful when you're trying to debug why something is not working the way it is. But this is probably the closest that you are going to get to directly seeing what's happening at the operating system level. Every one of those lines over there is a system call, right? And sort of translating that into which is translating the functionality of ls into something that actually finally ends up showing up on the screen, right? Other things, when you actually type the ls command, that's not part of the kernel. That's not part of the Linux operating system at all, right? In fact, ls is a separate program that is written as part of the GNU project and is used by Linux, among other things. Okay, so that's one part of it, right? So this is one way by which we can see the interaction with the operating system. The other thing that is interesting is, as I said, there are certain files. If I do ls in slash, what is slash? That's sort of the root file system of my entire machine, right? I see that there are many different kinds of folders over there. There's a folder called bin. There's another one called etc. There is home, of course, inside which I actually have my files. This initrd.ing is, well, it's actually a file which is part of the initial booting process of the system. You're not going to worry about that. What is interesting is these two file systems, dev and sys, right? Both of which I have talked about earlier. So let's go inside the /dev file system, right? And this is the nice part about it is it's just like any other folder anywhere in my machine, right? I see a bunch of files. I type ls and it shows me a bunch of files. What you can see is the colors that it shows you are a bit different than normal files. And if I type ls -l, I'll find that there are certain things. For example, this first character that I see over here, right, on the left, it starts with C. That indicates that it's a character type device, right? There are others which start with P, which indicates that these are a block type device. For each one of them, you will see that there are, a pair of numbers out here. This is what we call the major and minor numbers. Like I said, those are more sort of for internal identification. The operating system automatically assigns them to different devices. You can see that there is a device corresponding to SDA. That's the actual disk on which the operating system is stored. There is another one called RTC, which I believe is related to the real-time clock, right? There is something else for the various serial ports, TTY and so on, right? You will see that many of them are already created. Does it mean the system actually has so many serial ports attached to it? No. These come up by default when the operating system starts, even if nothing is directly connected to them. So this file system, in other words, essentially consists of a whole bunch of different virtual device files, right? If at all you go and try to create something new out here by directly doing make directory or opening a file or something of that sort, you could do that. Thing is, it will go away once the system reboots, because this is getting populated by the system as in when you either create a new device or load a new driver, or when the system reboots by itself. Okay. Now, the other file system that is of interest is, as I said, /sys. Now, what do we see in /sys? Once again, there are a bunch of things saying, for example, block, right? And here we can see that block gives me access in turn to something called SDA, right? So I can look at block /SDA, and that in turn shows me suddenly a whole bunch of interestingly named files, right? For example, there is something which says something about alignment, offset. There is something with this sequence. There are events and so on, right? And it's not entirely clear what all of these correspond to. But what is actually happening, as I said, is these are not real files. There is no data corresponding to this. This is a view into the operating system. What the operating system sees of the block device SDA, which it has labeled SDA, right? SDA is not a name that belongs to the disk as such. The Linux operating system, when it comes up, assigns a name to every disk that it sees, and one of those is called SDA. Now, the driver corresponding to that disk exposes a lot of useful information about the disk, right? Among other things, you can, for example, see something like there is something called size over here, right? And we can check what is contained in that. So if I look at using the command cat, which after all is just used to get the data corresponding to a file, I can ask for SDA /size. and it actually tells me this number, which is basically the number of sectors present in the file, right? In this case, each sector, I believe, is 512 bytes. So half a kilobyte. So this is basically 67 million half kilobytes, or 32, or roughly around 33 gigabytes, which we can check, and we can see that yes, the number of 1K blocks in the system is around 30 million, right? Which more or less corresponds to, but not exactly, because various other things. What is reported as the disk space used over here is typically less than the raw disk space that is available in the size, because the operating system sort of uses ability space for extra storage and provides you with a little less for actual usage. Okay. So we can see that what has happened over here, this file block SDA size, right, is something which seems to be actually querying the disk, getting some information back for you, and then reporting it for you in a manner that is human readable, and you can actually use even for, within your other programs in order to find out the size of the disks and so on. Okay. So what else does this have? We can see that, for example, it has a bunch of things corresponding to power consumption. There are different things related to devices and so on. Okay. Now, why would we use all of this? As I said, it provides a nice human readable interface into the kernel, because otherwise I can't really go inside and look at the various data structures that are present inside the kernel. This translates all of that into a form that I can actually read and understand a lot about what my system actually contains. So now that we have seen a little bit about the /dev and /sys file systems and the strace function call that can be used in order to visualize the system calls that are being executed when a program runs, right? Let's look at what a very minimal type of device driver looks like. So the code for this demo essentially consists of just one C file, right? There is also what this make file out here, which all of you should be familiar with at this point. The purpose of a make file is simply to compile, right, a given program into some kind of an object file or into an executable. Now, if I look at this make file, you will find that it's actually a sort of strange looking make file, right? It pretty much just tells me that there is this, it defines a variable called kdir, right, which is /lib/module/ and what is this command out here? It basically says run the command uname -r. Let's see what happens if I run uname -r on my system. It tells me the exact version of the kernel that I'm currently running, right? So this is a standard function. So what this thing out here, the shell uname -r does is, in the make file, it actually runs this uname -r command and puts the result of that out here. So in other words, it's telling me that this kdir is a variable which I'm defining in my make file, which corresponds to /lib/module/ whatever was the result of this, right? 6.12.43 plus get 13-AMD64. So there will be a folder with that name, that /build rather. And when I type the make command, it's actually going to run make in that folder, because I'm giving this -C command out here. Okay. So even though I'm typing make out here, it's actually going and running make somewhere else, right? What does that mean? It means go look for a make file in this folder, and that make file will have a lot more information on how to compile a module. I'm not going to go and look into that make file right now. It's a fairly complicated make file. It's not necessary to really understand how it works or what exactly it does at this point in time. Feel free to look into it. Of course, it's always good to experiment and read more about it, but it's not required in order to understand how compilation works at this point in time. So the long and short of it is, when I type make in this directory, what should happen is that it should go and check a make file which is present in this directory corresponding to the kdir variable and run the command make modules out there. What will that do? it basically looks for this variable called obj-m, right? And it says, okay, I need to create a .o file called vregdemo.o. Now, how do I create vregdemo.o? I need a vregdemo.c file for that. And yes, sure enough, it turns out that there is a file called vregdemo.c present in this portal. Okay. So what the make command is going to do, in other words, is to actually compile this vregdemo.c into an object file, but a special kind of object file. It will be having some specific structure which the kernel can understand, right?